Boo Show again. Today I'm going to show you how to diagnose a no crank condition on a 97 Honda Accord. But you can use the techniques shown here to diagnose a no crank on any vehicle.
First thing I'm going to do is verify the issue. The vehicle won't crank, so I'm just going to turn it to start, see if I can get it to crank. I'm in start. Nothing's happening. You can actually hear the fuel pump running when I'm in start. Now the next thing I like to do is either turn on the headlights or look at the dome light while I'm in the start position and see if it dims. I'm in start. I'm in start. I'm in start. You can see the light's not dimming. You could also use the headlights, see if they dim when you're in the start position. And you can see they're not dimming.
The lights not dimming means that there's no heavy load being applied to the battery. A starter motor consumes hundreds of amps. This large current draw will cause battery voltage to drop and the lights to dim. Another thing you may have noticed is when in the start position there was no click from the starter. A clicking sound from the starter solenoid could indicate a low battery, high resistance connection, or locked engine, due to a broken timing belt, for example. When in doubt, try to rotate the crankshaft with a socket and ratchet. If you can't turn the engine over, the starter can't either.
What I'm basically saying is, the fact that the lights don't dim is telling me that the battery isn't the issue. It's not a low battery. But in an effort to be complete, I'm going to show you how to test the battery. There are two methods.
One method is to use an inexpensive tool called a load tester. The second method is to use a conductance tester. You hook it up to the battery, enter the cold cranking amp rating into the tool, and it will perform a test to determine the battery's actual cold cranking amp rating. If the two numbers are equal, the battery is good. Before checking the battery, check the battery terminals to see if they're loose or corroded. If the terminals are corroded, remove them and clean the posts and terminals with a battery terminal brush until you're down to bare metal. If there are heavy deposits, you can use a solution of baking soda and water and finish up with a wire brush.
The first way to test a battery is like this. This tool costs maybe $20-30 bucks. It's called a load tester. It's pretty simple. You have an analog meter here, a resistor, and a switch. You flip the switch on. This resistor gets placed between the two terminals of the battery. It applies a 100 amp load on the battery, and the meter monitors the voltage drop. You'll see right here, there's a green zone and there's numbers, 200, 400, 600, 800, 1000. Those are cold cranking amps. So basically when you're applying a load to the battery, it should stay in the green zone for the cold cranking amp rating of your battery. So to find that, you look on the battery, and you'll see right here, cold cranking amps, 750. So when we perform our load test, we should remain in the green zone by 800. You don't want to do this for more than 10 seconds because this is a resistor and it will get very, very hot. See right now it's indicating no load voltage because the switch is off.
With the vehicle off, you should see around 12.6 volts on a fully charged battery. The meter on the load tester reads about 12.2 volts. But I've been performing checks on the vehicle, including holding the key in the start position, which caused the fuel pump to run, which drained the battery somewhat. If your battery is low, you'll have to charge it before performing the load test, or the tester could falsely indicate a bad battery.
Now we're going to perform the load test. I'm going to flip the switch here, hold it on, and monitor the voltage drop. Now again, this battery is 750 cold cranking amps, so it should stay within the 800 range. Again, you want to do this no longer than 10 seconds.
Considering that it was a little bit discharged and that it still stayed in the 800 cca range, this battery is good. Before we start testing the starter itself, we have to understand the circuit surrounding it. The starting circuit I fully drew out here is for this 97 Accord and can be found on 94 to 97 Accords. I'll explain a few basic start circuit designs here, and with the knowledge of the basic layout and components, you'll be able to interpret the wiring diagram of a start circuit on your vehicle. Here's how the starter circuit works. Before we talk about the circuit though, I'll briefly go over what a relay is and how it functions. A relay is basically an electrically controlled switch. A simple relay has 4 connections. 2 coil connections and 2 load connections. When power and ground is applied to the coil, a magnetic field is produced that causes the contacts on the load side of the relay to close. The starter solenoid serves two functions: to connect battery positive to the motor through its load terminals, just like a relay, so you have power coming from the battery through this wire, through the closed contacts, and to the starter motor itself, so it can rotate and crank the engine. The solenoid also pushes out the pinion gear, as shown here, which will engage the flywheel. This is where the starter solenoid differs from a relay. There are two windings on the solenoid: a pulling coil, which is right here, and a holding coil, which is over here, while a normal relay has just one coil. The solenoid is activated when 12 volts is sent from the ignition switch. You can see here's battery positive. When you're in the start position, 12 volts goes through here, goes through this switch. Just ignore that for now. And then goes down to this wire and into the solenoid. I call this the solenoid trigger wire. When 12 volts is applied to the trigger wire, two circuits are completed: one through the pulling coil and to ground through the windings of the starter motor, and the second through the holding coil and to ground through the solenoid casing. A metal plunger in the solenoid, which isn't shown here, is pulled in against spring tension by the magnetic field produced by the pulling coil. This pulls on a linkage that causes the pinion gear to come out and engage the flywheel, as shown here. The same plunger in the solenoid also simultaneously closes a set of contacts, these right here, to apply positive battery voltage to the starter motor. So you have power, they flow through here, through the closed contacts, and to the starter motor. At that moment, when the contacts close, the pull-in winding is kicked out of the circuit. So in other words, it no longer functions. And why that happens is because with these contacts closed, you have 12 volts on this side of the coil and 12 volts on this side of the coil. So there's no path to ground. There's no complete circuit. Therefore, the only winding still in circuit, as long as the ignition switch is in the start position, is the hold-in winding, which is grounded through the solenoid housing, keeping the pinion engaged to the flywheel and the contacts closed, supplying power to the starter motor. That's why it's called the hold-in winding. Its job is to hold the solenoid contacts closed and to keep the pinion out after the pull-in winding is kicked out of the circuit. When you release the key from the start position, 12 volts is removed from the trigger wire, the pinion retracts, the solenoid contacts retract via spring tension, and the starter motor stops rotating. Now, you'll notice in series with the trigger wire is a switch. This is called the neutral safety switch. It prevents you from starting the vehicle when it's in gear. On automatics, it means the engine won't crank unless you're in park or neutral. When in park or neutral, as you can see it's drawn here, the switch allows 12 volts to pass to the starter solenoid. When you're in any other position, the 12 volts will not be present to the starter solenoid, and the engine won't crank. Some vehicles use a relay instead of using a switch directly to interrupt power through the solenoid trigger wire. This relay is known as a starter cut relay. Here's an example of a starting circuit with a starter cut relay. When the ignition switch is in the start position, 12 volts is applied to both the relay coil and the relay load contact. So imagine this wire going to here. The safety switch is on the ground side of the relay coil. If a shifter is in the neutral or park position, the relay coil is grounded through the switch, as shown here, and when you turn to the start position, the relay will activate because you'll have power from the ignition switch, ground through the neutral safety switch. The relay will activate, pull the contacts closed, and 12 volts will pass to the starter solenoid. Imagine this wire going here. If a shifter isn't in the proper position, ground to the relay coil will be absent, the relay contacts won't close, and the 12 volt trigger voltage won't get to the starter solenoid.
Here's another circuit you may encounter. It still uses the starter cut relay, but it's wired up a little bit differently. Here's battery positive. Over here you have a constant 12 volts to the load side of the relay. On the other side of the relay, you'll see that you have your starter solenoid trigger wire. Here's your ignition switch. When in the start position, 12 volts will be applied to one side of the relay coil. But you'll see on the ground side of the relay coil, it goes into the PCM. Now inside the PCM, there's a driver. It's basically a transistor. When the PCM determines that the vehicle should be able to start, it applies power to that transistor, which is the equivalent of closing this switch and applying ground to the starter cut relay coil, which will allow the starter cut relay to close when you turn to the start position, which will send 12 volts to the solenoid trigger wire. Now, how does the PCM know whether you're in park or neutral? It uses the neutral safety switch. It monitors it directly.
Now it sends a voltage, a signal voltage, I don't know what the exact voltage is, let's say 5 volts, to the switch. When you're in park or neutral, it will connect this line to ground. What will that do? That'll pull that 5 volts down to 0 volts. If you're in any other gear besides park or neutral, say reverse, drive, second, or low, it will not connect that line to ground, and that line will remain at 5 volts. So why does any of this matter? Because the PCM monitors that wire. And based on the voltage available in that wire, it makes a determination. It knows if the signal voltage is equal to 0 volts, we're in park or neutral. And on the other hand, if the signal voltage is equal to 5 volts, we're not in park or neutral. So if we're at 0 volts, the computer knows we're in park or neutral. The driver in there will be activated, the transistor driver will be activated. That switch will close. It'll supply ground to the starter cut relay, and therefore when we turn to the start position, 12 volts will be applied here, we'll have ground here, this relay will close, 12 volts will flow to the starter solenoid trigger wire, and the engine will crank. Now if the PCM sees that voltage as being 5 volts, then it knows that we're not in park or neutral. Therefore, it will turn off that driver, ground will be disconnected from this side of the relay coil, and when we turn to the start position, we'll have 12 volts here, no ground here. This relay can't close, and 12 volts will not be applied to the starter solenoid trigger wire. Now that we have some background on how some common starting circuits function, we can continue. The next step is to check the solenoid trigger wire for 12 volts with the ignition switch in the start position.
The starter lives on the passenger side, right under the lower radiator hose. You can see it right there. And the solenoid, which we have to get to, is right there.
On the solenoid, you'll see 2 large wires, one going to the positive battery terminal and one going to the starter motor. The remaining smaller wire is the solenoid trigger wire.
You'll see up top is the 12 volt trigger wire, and down low, that's the 12 volt cable
that comes from the battery and supplies power to the starter solenoid.
Before we perform a voltage drop test on the wires, it has to be done with the circuit loaded. In other words, the solenoid has to close the circuit to the starter. So the first thing I'm going to check is the trigger wire for 12 volts. Under here is a spade terminal. So just grab the boot and pull it back and off. There we go. In there you can see there is a spade connector. And you want to test that for 12 volts when the ignition switch is in the start position. Now, I don't have a helper with me, so I'm going to do this solo. Set your meter to DC volts. I have these convenient alligator clips on mine, so I don't have to hold the probes on the terminals. Hook your black lead to the negative terminal of the battery.
When using alligator clips on the battery terminal bolts like I am, make sure there's no corrosion between the battery posts and the terminals. If there is, you won't have a good ground for testing. If you're not using alligator clips, just put the tip of your probe directly on top of the battery post.
Hook your positive lead to that spade terminal. Just going to hook the alligator clip up to that terminal. Now, since I don't have a helper here, I'm just going to put the meter up to the windshield so I can see what's going on. So with the shifter in park or neutral, it's in park. I should read 12 volts when the key is in the start position. In start. And there is battery voltage. And you can hear the fuel pump running as well. The fuel pump will run as long as you're in the start position. Now, if I didn't see battery voltage here,
I'd first check the ignition switch and make sure when in the start position, battery voltage is coming out of the start wire.
then the next place to check would be the neutral safety switch. If you have a manual, then I'd look at the clutch switch on the clutch pedal first, then I'd check the clutch relay.
The following location of the neutral safety switch in access instructions applies to 94 to 97 accords.
To get to the neutral safety switch, which is located to the left of the shift assembly, open up the center console, pry up this cover here. Under here are the 2 screws. Remove those. Remove the cup holder, just pulls out. There's one more screw right there. And then you can remove the center console. How you do that is you pull up. You pull up from the back, and then tilt it out towards the back seat. So you tilt it up from the back and then move it towards the back seat. That would remove that. Then you'll have two more screws exposed. One here, one here. You remove that. Then pull out the ashtray. And you'll have a final screw right there. Then you're going to have to shift out of park to get enough clearance to remove this trim piece. Shift it to neutral or drive, make sure the parking brake is up. And it's basically just secured with trim clips from there on in. So what you do is you start from the bottom. You lift this bottom piece up and pull back. The clips will disengage one by one. And then you'll have a bunch of connectors to remove. You'll have the connector for the four-way flashers, the clock, and one down here in this area for the cigarette lighter and the light in the ashtray. Then you could pull out this trim piece, and then you'll have access to the white plastic neutral safety switch.
The location of the neutral safety switch will vary from vehicle to vehicle, but the two most common locations are around the gear selector or on the transmission. Battery voltage being present at the trigger wire tells us that the ignition switch start contacts, the neutral safety switch, and the trigger wire leading up to the starter are all good. The next step is to perform a voltage drop test.
Okay, since I'm working alone, I'm gonna have to rig a remote starter switch here so I can do the voltage drop test, but before I do, I'm gonna turn the key to the on position. Now, if you had a helper with you, you could have them hold the key to the start position while you perform this test. I don't, so I'm just gonna leave it in the on position and remotely trigger the solenoid from outside.
The purpose of the key being in the on position is that I want to load the ground just as it would be before you normally turn the key to the start position.
Now here's what allows me to work alone. It's called a remote starter switch. It's pretty easy to set up. You saw I removed the solenoid trigger wire earlier. So I hook one end to the starter switch up to the positive terminal of the battery, and the other up to the solenoid terminal. Now the alligator leads on these are pretty large, so basically I got a thick gauge stranded copper wire with a spade connector clipped on the end of it and just hooked it down there onto the solenoid. That comes up, hooks onto this alligator clip on the starter switch. Now obviously you can see how careful I was to make sure that this doesn't touch anything grounded. Be very careful of that. And you'll see there's a light here to indicate that the circuit is complete and the switch is ready to go.
So pressing this switch would be just like someone was in the vehicle turning to the start position.
So first we're going to do a power to power voltage drop test. Turn the meter to DC volts again. Connect one lead to the positive terminal of the battery. And then we're going to connect the other lead to the positive terminal on the starter. Now you don't want the terminal that goes to the motor, you want the terminal that comes from the battery. And on this particular starter, you'll see it right there covered by a rubber boot. Right here. So you just grab that little tab and just pull it off. And you can see it's right there. There it is. So that's all I'm going to be doing is touching my meter probe to that terminal right there. Like that. When I squeeze this switch, we should see no more than 0.7 volts on the meter. You can see we're not getting response, we're not getting anything.
The reason we're getting no voltage drop is because the solenoid contacts aren't closing, as you can hear. This is preventing a complete circuit, and if a circuit isn't complete and current isn't flowing, you can't obtain a voltage drop reading. It may be easy to just condemn the starter at this point, but remember, the solenoid and starter both use block ground. So if there's a high resistance ground connection, that can cause the solenoid not to click, the starter motor not to function, or both. So continue with the ground voltage drop test before making that determination. Some people may point out that I didn't check the voltage drop at the motor terminal on the solenoid, and this is because the starter and solenoid are usually diagnosed and replaced as a unit. If one or the other fails, cost-wise, it's more practical to replace the starter. In addition to that, on this vehicle, the solenoid wasn't functioning and I couldn't take a voltage drop reading anyway. If you'd like to check the voltage drop across the solenoid, just move your probe from the battery positive terminal on the solenoid to the motor positive terminal. Remember, only perform this test if your solenoid is mechanically functional. Using the process of elimination, if a trigger voltage is present at the solenoid when in the start position, the power voltage drop to the solenoid is good and the ground voltage drop to the starter case is good, the starter or solenoid is bad.
I'm going to switch my meter lead from positive side of the battery to the negative side.
Then touch your other probe to the unpainted metal end cap of the starter. The max voltage reading you want to see on the ground side of the starter is no more than 0.2 volts.
We're going to do the same with the ground. That voltage drop is nowhere near where it should be. It's not high, but when the starter is loading the circuit, it's going to be higher than that.
That small change on the meter is from the solenoid hold-in winding being energized. That confirms this starter's bad and needs to be replaced. The cause of the no crank is either an open pull-in winding in the solenoid, worn brushes in the motor, or an open in the motor armature. The pull-in winding gets its ground through the starter motor itself, which is why a bad motor can cause the solenoid not to function. You may also ask, how do you know if the power ground connection to the starter is open? And the answer to this is right on your meter. When you turn your meter to DC volts and move your probe leads, you'll notice a fluctuating reading on the display. When you connect your probes across either the power or ground side of the starter and shake the leads, the reading should remain stable if the connection isn't open. If you connect your probes to the power or ground side and the reading fluctuates when you shake your leads, the power or ground connection is open. Make sure your probes are on clean metal, as a bad connection between your probes and the connection under test can cause a fluctuating reading as well.
Now to show you what I just explained with my meter set to DC volts, I'm going to take my leads, shake them, and you'll notice the voltage reading fluctuating. Okay, so now I'm going to set up my meter to measure ground voltage drop. Hook one of my leads to battery negative. I'm going to touch my other probe to the body of the starter. You'll see the reading still fluctuating. But the instant I touch to the starter, it's stabilized. Now I'm going to take my leads and shake them, and you'll see that reading is not fluctuating. What that means is that the ground connection isn't open. Now I'm going to remove my probe from the starter ground, and I'm going to shake my leads, and you can see the reading fluctuating. So if I had my probe on starter ground right now and I saw that, that means that the ground to the starter is open. You could perform the same test on the battery positive wire that goes to the solenoid.
I cover the replacement of this starter in another video. You can find a link in the description. Now I'm going to show you what the voltage drop on a new working starter looks like. I've disconnected the power to the fuel injectors so the vehicle won't start. Again, just like before, the ignition switch is in the on position to load the ground.
Now first we're going to start by doing a positive to positive voltage drop test. I'm going to attach one of my meter wires to the positive terminal, again set to DC volts. And I'm going to touch my other lead to the positive terminal
on the starter solenoid. On the power side, you should see no more than 0.7 volts.
When I activate the starter, we'll load that wire and the voltage drop will be displayed on the multimeter. And that's a good wire. We're going to do the same thing on the ground side of the circuit. Now I'm putting the black lead on the negative terminal just so the multimeter doesn't show a negative number. That's the only reason. It doesn't matter which lead goes where. Just be prepared if you reverse them that the multimeter will display a negative.
Then touch your other probe to the unpainted metal end cap of the starter. The max voltage reading you want to see on the ground side of the starter is no more than 0.2 volts.
Here it is. Ground voltage drop test. And that was under 0.2, so that ground is good.
The voltage drop on the power and ground side of the new starter is within spec, and the engine's cranking again. That's a fix.